But kind of the whole purpose of this video that I want you to understand is when you build a rollup, you need to give that rollup some kind of an execution environment. Meaning you need to give the rollup, if you're building it on Ethereum, some way so that it can read Ethereum bytecode and execute it. Because that's how it's actually going to be able to process those transactions that are being sent to the rollup. Hello everyone, this is Wintercode, and today we're going to be looking at Ethereum bytecode and specifically how it relates to rollups. So I've been going through the internet and trying to find good examples of rollup projects that I can study. However, it's pretty hard to find anything that's like a good starter rollup. Most of the stuff I find, it's within like Optimism's repo or within Polygon's repo, and it's pretty complex. It's not really something you can just sit down and build upon. So in today's video, we're going to look at rollups, and we're going to look at one of the most fundamental things that a rollup can do, which is execute code. So it's actually why you use a rollup. So in order to understand what executing code is, let's take a look at what Ethereum bytecode looks like. So I've got Remix here in front of me, and I'm looking at their standard storage Solidity smart contract. So I haven't really looked at this thing before, but it looks like it lets you store a value on the blockchain, a number, and it lets you retrieve that value from the blockchain. So I have this smart contract locally, and I'm using this version of the Solidity compiler. So I'm going to go ahead and use the Solidity compiler with the combined JSON flag. And for starters, let's just give it ABI and say storage sol. And we can see here what it's spitting out is the ABI for the storage .solidity smart contract. Another option that we can pass, which is maybe a little bit more interesting, is ASM. Okay. So actually, let's do that. Let's pipe it into a file called out.txt. We have kind of a bunch of these, like mstore, call value, push, mostly mstore's call values, pushes, some pops in here, some returns, some swap twos. And what these are is these are opcodes for the Ethereum virtual machine. For example, push should be in here somewhere. There's actually a few different pushes depending on how much data you want to push onto the stack. The Ethereum virtual machine is what's known as a stack-based virtual machine instead of a register-based virtual machine. But what is important to understand and why I'm showing you this is when you write a smart contract like this, what happens is you have to compile it. And you can actually see in Remix, there's a Solidity compiler. You can say compile it, and now it says, hey, look, I'm happy I compiled correctly. But what actually happened there was internally, within Remix, it produced something like this. It went ahead and ran probably a similar command to SOLC, the Solidity compiler. It would have produced some kind of output, probably multiple things like ASM, binary, and whatever that other one was. Oh yeah, ABI. And that's what it's actually, some combination of that. The binary is what it's actually going to write to the Ethereum network. So that way, the virtual machine on the Ethereum network, the computer, will know how to run your smart contract because it doesn't read Solidity, it reads binary data that encodes these opcodes for the Ethereum virtual machine. If you've ever worked with a programming language like Java before, similar concept. When you want to run something on the Java virtual machine, you have to compile your program into Java bytecode. That's why you have languages like Java, which compile to Java bytecode, but you also have languages like Scala, which can compile to Java bytecode as well. And you're seeing more and more like cross-compilation tools these days for things to run on different environments. It's kind of the same reason why like you can't take a binary that was compiled for an Intel processor and run it on a different processor architecture. Those kinds of things. The same concept applies to blockchains and blockchain virtual machines as well. So if you took bytecode that was, say, compiled to run on Solana's virtual machine and tried to plug it into Ethereum, it wouldn't work. Now what happens is here, also in Remix, just out of convenience, if we deploy it to an environment, like I think the default here is this Remix VM, so it's simulating an Ethereum virtual machine. Like if we deploy, we can see here, it actually was deployed. There's some stats on the smart contract getting sent on the blockchain. But we also have this debug option, which is really cool. And you can see over here, there's some stuff like call data. There's actually a lot of stuff to get into here. There's a stack as well. Remember we said the Ethereum virtual machine was stack-based. That's why you're seeing pushes and pops in the instruction set. We can see here, this is all of the bytecode, the opcodes, that make up this smart contract. So this should be very similar to what we were seeing here. Some pushes, there's an M store, and yeah, we see that, right? Push, push, M store. And the reason that's important is currently with Ethereum, when you write a smart contract and you deploy it to the L1 mainnet, all of this code is running on the L1. If you remember, like the high level kind of abstract view of Ethereum is that it's a state machine, meaning it has some state of memory, and that state of memory can be updated. For example, if you trade an NFT to somebody else, something in the Ethereum state needs to be updated to reflect that that NFT now has a new owner. The thing that causes state transitions or state updates in Ethereum is transactions. But anyone who's interacted with Ethereum knows it has high gas fees, meaning for you as a user, it's expensive to get your transactions processed. It can be quite a bit of time before your transaction gets put into a block and processed. Block times on mainnet are about 12 seconds, so you get a block every 12 seconds. So part of the reason why rollups, these kind of L2 scaling solutions, are so attractive is as a user, you could send your transactions to the rollup. The rollup bundles the transactions, it executes them, and then it sends the results of the execution to the L1, to the Ethereum mainnet to be stored there. But kind of the whole purpose of this video that I want you to understand is when you build a rollup, you need to give that rollup some kind of an execution environment. Meaning you need to give the rollup, if you're building it on Ethereum, some way so that it can read Ethereum bytecode and execute it. Because that's how it's actually going to be able to process those transactions that are being sent to the rollup. Remember, the whole point of a rollup is it's gonna kind of act like the execution layer. You're going to send transactions to it instead of the mainnet. It is going to interact with the smart contracts and execute all of these opcodes required to process those transactions. So that's all I really wanted to do in this video, is just talk about what bytecode is, what a virtual machine is, and why when you're building a rollup, you need to have a virtual machine. It can be like a standard Ethereum virtual machine. What you see these days mostly are optimistic rollups, which we may look at next time. You can read up on those. And then there's also ZK rollups, which run on ZK or zero knowledge EVMs. And ZK rollups have a little bit more of a computational overhead to them because they require zero knowledge like proofs. But they have what's called faster finality times, meaning once you've generated the proof and the network accepts it, your transactions are done. There's not like any chance of them getting rolled back. Optimistic rollups do not go through that proving step. They kind of assume that the transactions are valid by default, which means that there's kind of a longer waiting period for somebody to submit what's called a fraud proof and basically contest whether or not a transaction or a block was done correctly. So what that means to you as a user is it can be days before you really have confidence that your transaction has been settled or not. In the next episode, I'm actually going to start building like the smart contracts required for a rollup, and we'll start looking at some different kinds of architecture. Till next time, have fun, keep building, bye.